The wing area is the planned surface area of the wing and has the symbol S for surface. It is deemed to include any part of the wing covered by engine nacelles and the part of the fuselage in line with the wing, since the pressure pattern carries over these areas, allowing them to be legitimately considered as part of the entire area. The wing span, lowercase b, is the distance from wingtip to wingtip, usually now quoted in meters. The chord is the distance from leading edge to trailing edge, and the average chord, lowercase c, is the geometric average. The product of the span and average chord is the wing area. The aspect ratio, or AR, is the proportion of the span and the average chord. That is, B over C. If the plan form is curved, for example like the Spitfire's elliptical wing, an alternative way of determining the aspect ratio is span squared over area. This assumes, of course, that you have a figure for the wing area. The aspect ratio of the wing determines the aerodynamic characteristics and structural weight. For example, a wing area of 100 square meters could be arranged in a high aspect ratio, here 51, or a low aspect ratio of, say, 3. Typical ARs vary from this value for a modern combat aircraft, through 12 for a high-speed jet transport, to 35 for a high-performance sailplane. Continuing with the terminology, we have root chord, which is the chord length at the wing centerline, denoted by CR. Logically, at the other end of the wing is CT, the tip chord. The ratio between these two is known as the taper ratio, CT to CR. The taper ratio affects the lift distribution and the structural weight of the wing. Ratios range from 1 for a rectangular wing to 0 for a delta wing with a pointed tip. For a swept wing, the sweep angle is usually measured as the angle between the line along the wing joining points of 25% chord and a line perpendicular to the root chord or aircraft centerline. Finally, the mean aerodynamic chord, abbreviated to MAC or MAC, is the chord drawn through the geographic center of the plan area. It is located at the reference axis of the aircraft and is a primary reference for longitudinal stability considerations. A rectangular wing of this chord and the same span would have broadly similar pitching moment characteristics. So far in these lessons on lift, we have considered only two-dimensional airflow, and a sound understanding of this is the foundation for a full appreciation of the actual pattern of airflow around an aircraft. Even small changes of pressure will modify the airstream direction by inducing flow towards any region of lower pressure. This three-dimensional airflow can modify the angle of attack, creating an effective angle of attack. It may increase drag and alter stalling characteristics, and can even influence the control and stability of the aircraft. From now on, instead of just the aerofoil section, we will be considering the entire wing. And as a precursor to the next few lessons, you will need to be familiar with the terminology associated with wings. As mentioned in the last lesson, the third dimension in the airflow over a wing, lateral flow, is created by pressure differentials. Air flowing over the top surface of a wing is at a lower pressure than that beneath, which can be at a pressure similar to, slightly higher or slightly lower than ambient, depending on angle of attack and wing section. The pressure differential induces spanwise flow from high to low, towards the roots on the upper surface and generally towards the tips on the lower surface. The trailing edge and wingtips are where the airflows interact. The crossover of the inward flow on the upper surface and the outward flow on the lower surface at the tips and trailing edge form vortices, particularly at the tips, where air can spill around them to the low-pressure area on top. By convention, the wing is viewed from the rear, so the vortex at the left wingtip rotates clockwise, and at the right wingtip anti-clockwise. The arrangement of the forces can be seen with the vector triangle. At higher angles of attack, with a lower IAS, the shape of the triangle will change. As speed decreases, the chordwise vector will shorten, and the spanwise vector will lengthen, with the greater pressure differential that is creating the increased lift. The result is stronger wingtip vortices. In a more pictorial representation, the change of vortex, form, and strength with speed is shown on the screen. The general pattern of the vortices is also shown. Trailing edge vortices create certain vertical velocity components in the airflow near the wing, both behind and in front of it. These vertical velocities cause a downwash over the wing, which, in turn, causes a reduction in the effective angle of attack. As the vortices increase in strength with increased angle of attack at lower speeds, there is further reduction in the effective angle of attack. Because of this local reduction in effective angle of attack, the overall lift generated by a wing will be below that which would be generated if there were no spanwise pressure differential. It is, paradoxically, the production of the lift itself which reduces the magnitude of the lift. To replace the lift lost by the increased downwash, the aircraft must be flown at a higher angle of attack. If the vortices were absent, the lift vector would be at a right angle to the free stream relative airflow. But with the effective airflow created by the vortices, the lift vector is tilted back and creates drag, known as induced drag. The stronger the vortices are, the greater is the induced drag. Wingtip vortices, in particular their influence on upwash and downwash, have significant effect on several important areas of aerodynamics, stability and control. Some of these effects will be examined in the following lessons.